Ladies and gentlemen, please welcome Andy and Neil.
They look like always first round Mark 1, aren't they?
And the Delta, just a couple seconds, 4 to be exact, and we're rushing out New Zealand. We'll be cheering huge right now. The first race of the America's Cup goes to Emirates Team New Zealand.
Good evening, everyone. It's really great to be here tonight. This is our first lecture of 6, and hopefully we'll give you a little insight into some of the technology behind America's Cup boats. Obviously it's a very big topic and we have a very short period of time to talk about it, so we're going to focus on the foiling aspects of the boat. So that's what we'll talk mostly tonight about. So as I said, my name's Andy Kensington. I was part of the Emirates Team New Zealand design team. My background is in structural engineering, or the composite structures, and as I said, we're not going to talk a lot about that tonight. We're just going to focus on the foiling aspects. So we'll go through sort of the development of Team New Zealand's foiling program. We'll talk about Team New Zealand's design team, how that was structured, a little bit of background to the AC-72 class of boat, and a little bit about the physics of sailing, some of the sailing craft you'll see out there. So some of these slides I'm going to flick through pretty quickly, just due to the time that we have available, but feel free to save up some questions and there'll be a question time at the end of the evening. Okay, so the 34th America's Cup in San Francisco. This is the first time with a new class of boat, the AC-72 class. It's a Catamaran class, and it opened up, it was a box rule, so there was basic length of 72 feet, a beam of 45 feet, displacement 7,400 kilos, and so that compares to 24 tonnes for the class of boat that was used in Valencia in 2007. The boats were powered by 40 metre high rigid carbon fibre wing masts, 11 crew, so they were very undercrewed. There was very few crew and the demands on the crew were quite intense. The boats were potentially able to do up 30 knots upwind and approaching 50 knots of boat speed downwind. The class rule was structured such that it was difficult. I think the rule designers made it difficult to fly a boat fully. I think they thought there'd be foil assisting, but not fully flying. And so there's some leeway in the rules, and that's sort of part of what we do as designers, is try and look at the class rule and work out how we can do what we want to do. So the Emirates Team New Zealand design team, so we'd come from a monohull background, so we had a lot of experience with the old class of boat, right through from sort of the 95 days, right through to 2007. They were in the same class of boat. There had been slight changes to the class rule, but it was basically the same boat, and so there was quite a lot of information to draw on for 07. So moving into this new class of boat, it was a fresh, clean piece of paper. Everything was going to have to get designed from scratch. There was no drawings to pull out from previous designs or boats. So the design team was very big. As a consequence, we had 28 full-time people in the design team, so engineers, naval architects, scientists, and they were there for 3 years pretty much. During the peak, we're sort of about 35 strong during the production of the 2 boats. To boost our knowledge of multi-hulls, we needed to bring in some experience from multi-hull design, so we brought in a number of people who were leaders, international leaders in multi-hull design, so they were sort of brought into the team and became a key part of our design team. And we also had people from the aerospace and Formula One industries as well. About 25% of the team's total budget was allocated to research and development. Another factor was for the challenges that we knew we'd be up against it. Oracle had already been through a D to GIF challenge in 2010 with their wonderful large trimaran, wing-sailed trimaran, and so that put them in a pretty strong position starting this event. And I think that's what put a lot of potential challenges off challenging for this event, was that they just could see it being very, very difficult to be able to compete with Oracle. Okay, so we're just going to flick through a few slides on some boats that you might see out there and just talk a little bit about some of the sort of what's going on there. So this traditional keel boat, so these have been used in the America's Cup, up until 07. There's been a dealer gift challenge with Dennis Connor's Catamaran in 88 that you'll probably remember, and the 2010 match. But other than those two events, they've been monohulls, and so you have heavy ballast keel down here. The boat leans over, the centre of buoyancy will sort of move to leeward here, and that's sort of what creates your riding moment to counteract the sail force here. So these boats are pretty limited, their speed is pretty much limited by their waterline length. So you're dragging around a whole heap of lead in this NZL 92 here. So she weighed 24 tonnes, so 20 tonnes of that was lead right down here. So you've basically got to drag a lot of weight around with you to get through the water. So the speeds were, 92 would sort of do about 10 knots upwind, and that's, pretty much harder to get much faster than that, pretty difficult. The boat over here, Reliance, she's still the largest America's Cup boat ever to compete in the America's Cup, and that was a wonderful example of engineering at the time as well. But not a lot of, no change in the physics of what's going on between these two boats, really, just the material technology's changing to make them a little bit different. So a theme of the monohull is the Canting keel boat, and again, you'll be familiar with the Volvo race. This is Camper here, and Sydney Hobart winner Wild Oats. So you can sort of see here the bulb sticking out to windward. So what happens here is the keel's canted over up to 40 degrees each way, and so the distance between the centre of buoyancy and the centre of gravity of the fin becomes much larger, so you can have a much lighter bulb, and so this allows a much higher top speed. You need to use dagger boards on these boats due to you still need to resist the leeway component, so all these boats will have some form of dagger board which is deployed. You can sort of see the windward one lifted here. So multi-hulls. So multi-hulls been around for a very long time as well. Early Polynesian explorers were multi-hull craft. So here we've got rid of the ballast altogether. We've just got two lightweight hulls separated quite a long way, and so as the boat wind force hits the sail, the windward hull will lift out of the water, and so the centre of buoyancy is way down here, and the centre of gravity of the boat's up here somewhere, so you've got a very high righting arm, and you've got no lead to deal with, so the potential top speed of these boats is much, much higher. So Peter Blake, you'll remember, 94, set the Jules Verne record, 74 days, and so that theme's been continued, and that record is now sitting at 45 days for this one out here, Bank Populaire, which is pretty staggering. I think that's an average speed of around 30 knots continuously around the world. So it's quite amazing. This boat's foil assisted. It'll have curved foils in the floats, but it doesn't fully fly. AC-45, which was used in the World Series, that's a conventional, being wing sailed, but it's still a conventional multi-hull. So a foiled multi-hull, pretty similar to what we've just talked about, but now we've got this, we're starting to put some horizontal surfaces in here, and they start lifting the hull out of the water. So the potential speed is much higher due to the fact the drag is reduced significantly, and we'll talk about that in some detail shortly. But other than that, pretty similar principles at places. You need something to resist the side force. Your centre of gravity of the boat's up here, up to windward. And so here's a picture here of day 5 of our first boat sailing, and these two smaller boats over here. These have happened post-Cup, so it sort of shows some of the feed down effect that's happening already from the technology that's been developed during the America's Cup. This is a production boat, fully foiling 18-foot production boat, which you can buy off the shelf now and go whizzing around the harbour. And this is Team New Zealand's wing trimmer, Glenn Ashby, winning the A-Class Worlds in Takapuna this year. Okay, so some of the forces that are in play, you basically got sort of hydro forces and aero forces. So hydro forces just to do with the water, so anything that's in the water. So hydro lift and hydro drag, you have two components of each of these forces, and then aero lift and aero drag. So with a foiling boat, what's in the water is actually getting quite minimal, so you've just got the foils. So a lot of what's driving these ratios here is just the foils, and the aero is to do with the wing, the platform, so the hulls and the cross structure, anything that may be producing drag, so the crew even will be producing drag. So the name of the game is to minimise your drag and maximise your lift. So basically improve these lift to drag ratios of both of these hydro and aero things. So just quickly, the wind triangle that you see. So sailing, the wind is coming vertically down. So the true wind's coming vertically down here, both these cases. So your boat's sailing along up here upwind, and so the true wind's coming vertically down, but the apparent wind that the boat's seeing is at some angle due to the boat's velocity. And so with these really highly efficient boats, and a lot of high performance sailing craft have this, is that they'll downwind, they'll sort of jibe or tack downwind, so they don't sail dead downwind because they can actually make a better velocity made good to the mark by jibing. So you can sort of see here, the wind direction is still coming vertically down the page, but the boat speed component is so large here, the apparent wind is still actually coming forward of the beam of the boat, which is quite amazing. So that's why with the AC-72 class of boats, you never really saw downwind sails. They're all sort of tight luffed sails, and you hardly ever saw the code 0. Also, the wind direction was so far forward. Very little difference in sail setting, wind to downwind. Okay, so why did Team New Zealand have to foil? Number one, it would be faster. So this is a graph that was put up at an early sort of design team meeting that we had, and I'll spend a little bit of time with this one because I think it's quite important, and it sort of shows you the things that we were, the clues that we had and why we chased it. So up here we've got a lift to drag ratio, and across the bottom here is boat speed. Now these curved lines here are just different candidate hulls. So this is a typical lift to drag ratio for a catamaran hull, I guess. And what you've got here, this line going across here is a typical lift to drag ratio for a submerged foil. And so as you can see, at around sort of 20 knots here, there's a bit of a crossover. And by the time you're getting to 35 knots boat speed, you've got a massive advantage if you can be foiling. And so this 3 to 4 times reduction in drag just showed us that it was a huge loophole in the rule, and if we could make it work, you had to do it, because if someone else could do it, you weren't even going to be in the game. So, and it also wasn't a function of boat speed, upwind or downwind, it was just a function of boat speed. So if you're going fast enough, you could, foiling upwind or carrying amount of lift on your Daggerfoil would pay off. Another reason that we looked at it was that it would be safer. So an early VPP modelling of the AC-72 class, which is a velocity prediction program that all the teams would be running, each have their own programs. But our one was saying that it was actually very difficult to solve the equations for sailing downwind and more than about 18 knots of breeze, which means it's pretty impossible to sail the boat downwind unless you're carrying a significant proportion of lift on your Daggerfoil. It's a sort of common, it's quite a common occurrence to see a picture like here where the boat's tried to bear away or it's been hit by a gust and it goes over the front like that. So with the conventional multi-hull, you're just relying on the buoyancy of the bow to keep you up. You've got no lift from the board, so they're quite prone to this sort of fore and aft stability problem. So it was always good to look back at history and see what's been done in the past. So early foiling boats, so around the 1900s, sort of just as the internal combustion engine was sort of getting going and people were trying to work out how to stick them in boats. They were looking at ways of going fast, and since horsepower was pretty limited, their only option was to look at reducing drag. So a lot of people were playing around with foiling setups, and Alexander Graham Bell was sort of probably the most famous example of this, and this particular boat set a world speed record in 1919, of 114 kilometres an hour on water, which is pretty staggering when you think about it. That record wasn't beaten for many years. So it relied on these foils here, so it's a fully foiling boat, and we call these ladder foils. So there's like runs of a ladder, and each of these is a lifting area. And so the beauty of this system was, as the boat got faster, the amount of lift area would automatically reduce. So it was quite a stable setup. Since then, there's been lots of people doing it. In the 50s, we had a sailing boat here. Hydropter is sort of reasonably well-known French offshore multi-hull, and briefly held sort of world speed record, 52 knots. And the Moth, it's a single-handed 12-foot-long development class, which is now all the boats are foiling. And these boats are very, very efficient and impressive. They have T-foils, so it's a T-shape on the daggerboard and the rudder. And the helmsman has a lot of control. The daggerboard's angle of attack of the foil is controlled by this wand at the front, and so it's quite an active ride height. As the boat starts flying a bit too high, this angle on the wand changes, and it has a little linkage back into the bottom, and it changes the angle of attack on the horizontal surface. And the rudder is also controlled by a twist grip with the helmsman, so they can change the angle of attack on that also. Unfortunately, the AC-72 class didn't allow any such sort of automatic ride height control. There's no feedback loop allowed from ride height, so you couldn't say, oh, we're flying a bit high, wouldn't automatically adjust the angle. It was all had to be driven by the crew. There was no allowance for adjusting the elevator angle while racing, so it was all fixed before the start of the race. So Emirates Team New Zealand's design approach, so obviously theoretical and then testing on the water. So we did a lot of trying to prove our concepts on the water, and we chose we went to a 10-metre long catamaran we called SL33. We had 2 of these, and we did a lot of testing on the water with those. We also had a model test program at 3rd scale, which was sort of codenamed Waka, which we didn't test in a tank test in a tank in England. It was in a lake in the Waikato, towed behind a fizz boat. So all of these things were to try and overcome the inherent instability of a foiling multi-hull within the class rule, within the AC-72 class rule. Okay, so the pitch dynamic stability is critical. So fundamentally, it's quite an unstable thing to be doing. You've got a foil here, horizontal foil down here, and as you speed up, the forces on that foil will be increasing at the square of your velocity. And so basically, as you get faster, you'll put more force on here, and you'll lift more, and so that's going to pitch the boat up also. So you're going to, the bow's going to swing up also. So that's actually putting more angle of attack on this foil also, which is then getting you more lift. And it's a very unstable situation. What will happen is you'll sail along for a while, the bow will start lifting, you'll go faster, lift some more, and eventually the foil will stall, or it'll lift out of the water, and you'll crash back down, and that's called a wheelie, and we'll see some examples of that coming up. So there's things you can do to minimise that, which is keep the Daggerfoil area sort of close to the centre of gravity. You don't want this too far forward. It's less stable, and obviously elevators on your rudder will help with that as well. Okay, another issue or another problem with hydrofoils is cavitation. So that's when the surface pressure on the foil falls below the vapour pressure of the water. And when that happens, you'll get these bubbles appearing. So if you start getting bubbles, your drag's going to go through the roof, and you're going to start losing lift. And with these hydrofoil type boats, it's actually a very difficult problem to avoid at speeds of greater than 50 knots. And you're starting to have problems at 40 knots. So one of the things that would be limiting the top speed of these boats is you'll be into that 40 knot, high 40 knot area, and you'll be hitting parts of the board will start having small bits of cavitation, and that will actually be starting to increase your drag. And so that's sort of putting a bit of a limit on the top speed of these boats a little bit. You can design foils that can go above that speed, but they're rubbish for sailing upwind or at lower speed. So our designers spent quite a lot of time looking at the section design. So at the bottom here's a sort of an aerofoil shape. And this graph here sort of shows the pressure distribution along the aerofoil. So that's the surface pressure that you're getting, and that's at a lift coefficient of 0.5, which is a design lift coefficient for our daggerboard. Now what the guys are trying to do here is actually make this a very flat curve. So you can see it's got a very flat top. Most conventional foils on on sailing boats will have a very peaky pressure distribution, so you'll have a really high peak up here and it will sort of drop away, and that would be absolutely terrible for cavitation. So a lot of work was spent on foil section design and just ways of minimising. You can't stop it, but you can minimise it and delay the onset of cavitation. So this diagram just shows a bit of what a Daggerfoil sort of looks like. You've got roughly a pretty vertical section here, and that's predominantly to resist the side force of the boat sailing upwind. So you've still got quite a high side force that you have to resist. So this sailing upwind, most of this needs to be in the water. Once you start sailing downwind, the boats were lifting clear of the water. So all of this area down here is designed to resist cavitation and operate at a much higher boat speed. And so the section would be quite different throughout, from the section design through the top here to what you'd have through here, and this radius was very critical as well, was all tailored very carefully throughout the board. So it was a big job to decide on the section design for all of this. Okay, so now some of the fun stuff, the SL33 testing. So these are the 10-metre boats. We had 2 of them. We knew it would be a very sort of dynamic problem, so we needed to test it on the water. The sailors need to know what worked and what didn't and how they could overcome problems on the water. So this is a really good way of doing it. We were limited sort of by the protocol, the cup, to either be a 10-metre boat. It was maximum length, or you could use the AC45s. We chose 10 metre because it was still at a much smaller scale, and we could build boards relatively quickly and cheaply. So we tried over 12 different Daggerfoil designs with this program. Another advantage was, it didn't take up the whole team resource. When you went sailing, you could, four crew and a chase boat, and off you go. So it didn't take a lot of resource for the team. So we were able to do a lot of testing, and we learnt a huge amount from this, a lot. So the testing was still continuing while Boat 1 was under construction, and it led to changes to Boat 1 while Boat 1 was under construction from what we were learning on the water. So these boats, by the end of it, we'd sort of had over 35 knots boat speed out of them, which is pretty amazing for a 10-metre long boat. And there's 99 sailing days that we logged in the end with these boats, so they got a real thrashing. That they only went out when it was 20 knots plus of wind. There were no light days when they went sailing, so they got a real workout. So the Waka, so this is our tank testing. So the tank was a couple of lakes in the Waikato, the Karapia or Arapuni. And so again, this was a pretty valuable thing to try ideas. This is at a smaller scale again, and there were less people involved to run this program as well. So we were able to test different foil designs, different elevator designs, strakes on the hull, lots of different things here. So how this works is you basically got a tow rope here. This is going off to a small powerboat, and this is sort of at the centre of effort of a sail. And this is instrumented up here, so we know the angle and force on that line. We also had a pot, so there's still a helmsman on board, so you're still getting a bit of helmsman input into the system. But what you don't have is any sort of control on the rake adjustment of the Daggerfoil, so it is sort of set for a test, and then you run with that and then change it, try something else. In all, we did 23 days of testing with the Waka. Okay, so this is a bit of video of the progression of the SL33 testing. It's over a 12-month period, so what you'll see at the start is the boat sort of in its standard configuration, so just no lifting surfaces on the dagger board, and no elevators on the rudder, and then you'll sort of see a bit of a progression through it. Now there's a bit of commentary here from mostly from Joey Allen, who's our crew coach, and sort of been a bowman with Team New Zealand for years, and his voice sort of a bit of the excitement that was happening at the time, because each day we were going out, we're sort of learning new things. So a little bit of colourful language coming up. So this is the boat in its standard configuration. So not ideal. Okay, so now it's sailing with an L board, so still no elevators. An L board was a...
And I think Dino's bought
That's
lifted
the L
his
board
board.
there,
He's
that
got
boat.
best extension. Is net there?
Yeah, boat 2's extension is 1250. Its rake is still 4. Its cant is still -2.
So it's starting to get a bit of lift.
Has a rake of 3, a cant of 11, and an extension of 1750 with a seafoil.
Okay, so now first sail with an elevator, and this is when actually we started getting, making some real gains.
Whole thing's out of the water. We've done a rudder. Holy Jesus. We've done a rudder pitch. Rudder pitch change. Whole boat's lifting out of the water.
So yeah, pretty exciting days this was happening.
We're just smoking the other boat right now.
Yeah. So yeah, we're always out there with two boats. One would be in a standard configuration. Okay, so now we're trying to start to play with the rake control of the dagger board.
Nice fly here. This is a good one, guys.
And you watch closely, you'll see a wheelie coming up. So there we go.
Hey, that was one of the better ones, huh? Hey, write that time down. 2 o'clock.
So you see the boat would lift
Really
and
good
lift, the
fly,
bow would go
good
up,
fly.
and you'd stall the board and you'd crash back down again. Better to do it at this scale than at 72 feet scale. Okay, so system 2, that's just a variation of we're trying different rate control systems. Sort of getting more stable, but yeah, still a fair way to go. We're still using an L board at this stage, and we ended up not going that way with the final dagger boards.
Fuck, we sliced through those waves, nice.
4.5.
Okay, so we also did a lot of wing development with the 33s as well. So we built 2 wings for them, and they were basically half scale, about 48% I think of the actual wing that we did for the 72. And so that was a nice way to learn about. We had a leading edge twist feature which we used, so we learned a lot about it with this scale. And so we're able to sort of combine the foil testing and wing testing together. And so this is a shot now. It's getting pretty close to the design that the boats ended up happening. So getting pretty stable and just smoking along. So yeah, quite a progression from when we started a year earlier. Sailing really quickly in quite rough water there. No problems at all. So the Waka, it's a little bit of footage of that. So as I said, we're at the lakes in the Waikato, so you can sort of see the powerboat over here, and there's the tow line, and it's instrumented up here. And so this is steering at the moment. It's Pete Melvin, who's one of our naval architects of the team. And so from this, we're able to sort of learn about how the boat would handle leeway and things such as that. So here, this shot here shows we've changed the rake and the boat becomes unstable, so it becomes pretty unmanageable. You'll see. And again, much better to do at a small scale. So here's a bit of GoPro footage of the Daggerfoil operating near the surface. So this is sort of a concept that all the teams had in the end. So you're basically forming a bit of a V in here, and that's your lifting surface. So it makes it quite forgiving. So as the boat starts lifting too high, you get the tip here breaking the water, and you start losing area here as well. But the tip will break the water, and the amount of lift you're generating will reduce automatically. So it makes them a little bit more forgiving. Here we've got daggerboard 2. So this was the daggerboard we used when we launched our first boat, a scale version of it, and Glen Ashby steering here. And so this was quite a conservative design, and it was and we made massive leaps after it, but when we launched, we just wanted to be able to go foiling stably and just see if the concept was working. So here's testing on the water. So here's some GoPro of it, and you can sort of see this is quite aggressively breaking the water here. So it's quite stable. So as the boat would lift, the tip would come out and it would drop back down. So when we launched the boat, it was actually surprisingly quite easy to foil. I think the scale effects actually help you at the bigger scale. So that's all great fun, but eventually you've got to build a boat. You've got to start a race to do shortly. So we need to start building a boat, and these were massive undertakings. The amount of work was huge. So to build a platform and Daggerfoils, you're talking 45,000 man hours, and 20,000 man hours for the wing. So it was a huge undertaking. We had about 6 or 7 machine shops in Auckland building titanium parts for us. It was pretty full on, and I'm not really going to be able to talk too much about the construction side of things tonight, but it was a big undertaking. So we launched in July of 2012. We were the first team to launch their boat. We were foiling on day 3. No problems, and we did 30 sailing days with that boat, which was all you were allowed in that time period, and that's all the sailing that boat has done. At the time, we were sort of doing about 35 knots downwind and about 18 knots upwind. There was still all the aero fairings to come, so the boat was quite crude. The structure was there, but all the finishing hadn't been done. So we still had beam fairings to come and sort of wing sealing, so sealing between the wing and the platform was still to come. With this boat, we didn't get a lot of time to input into the final boat. We had about 5 sailing days with this boat before we sent the hull lines to start getting built for our second boat. So there wasn't a huge amount of time, but we were able to confirm basic things like the daggerwood location that was in the right place and the balance was right. So it gave us, and the foiling concept was working also. So the Daggerfoil evolution. So Daggerfoil 2, it was the one you saw on the Waka there. Daggerfoil 1, not there. So that was, we started building it, and then from things we were learning in the office and on the water with our SL33 testing, we sort of superseded it, and it was obsolete before we even had a chance to build it. So it didn't get built. So it was sort of an L-shaped thing over here, and the mould tooling got built, but we scrapped it. So we ended up launching with this sort of shape here, quite V'd, a bit of an S in here, quite a lot of lifting area down here. And sort of over the next 6 months or so, we were developing our designs, and by the end of the cup, by the start of the cup, I should say, we sort of had about 1.2 square metres of lifting area, foil area. So the board was a lot less stable, but the sailing team had mastered the boat, and the control systems were such that they were able to fly the boat happily with a less stable design, and it was obviously it was a lot less drag, so it was a lot quicker. So boat number 2 launched in February of 2013 in Auckland, and we sailed I think about sort of 25 or so days in Auckland before we had to ship out. So the changes there were subtle changes to the hull shape, but the boat was intended to be a fully foiling boat from day one. The beam design was pretty much the same as the first boat. So a lot of things were very similar to it. The development we did, you can see here the underwing fairing. So you're basically trying to end plate the wing down onto your platform here, and there were huge fairings on the platform to seal that against. That makes a huge difference to the efficiency of the wing. So that was things we were working on. These big fairings here, so they actually gave quite a lot of lift. So they were used to, they would help lift the boat also. And we had a couple of sizes of fairings there that you might have seen during the racing, which we swapped between. When it was windy, we had to sort of put a smaller one on, and in the more moderate conditions, we had these monsters. Other things, we worked on stiffening the lower flap here, so we were trying to stand the wing up more. So we sort of did that through the Louis Vuitton series. Obviously the crew had been working extremely hard, and so they were able to foil jibe consistently. A good foiling jibe loses you very little VMG to the mark. and they sort of got these roll tacks, foiling tacks going as well, which were quite cool to see. So yeah, a huge amount of work with the sailing team. I think we got records, and we did about, in the life of the two boats, we did about 2,000 tacks and jibes, I think, over that period. Yeah, so we made a big improvement from the end of the Louis Vuitton with Luna Rossa to the start of the America's Cup with the various things we did. So by now the boats were, we were constantly, very often 45 knots plus downwind, and our upwind speeds were sort of in the 28 knot plus range upwind. So, so in a less than a year, you're pretty much going 10 knots quicker than you were when you launched your first boat. Okay, so America's Cup final races. You all know what happened, so I'm not going to spend too much time here, but Team New Zealand started extremely well. We'd been through a Louis Vuitton series, although the challenges were very weak. It still puts you in a race mode, and I think we hit the ground running, and surprisingly we had a speed edge upwind, which was great, so that the team took full advantage of that and got off to a great lead. Through the middle of the regatta, Oracle were starting to make inroads and closing that gap, and then by the time we get to the last few races, they had sort of surpassed us upwind, and in the top end upwind conditions they were quicker than us. So here's my last slide I'm going to put up before I hand over to Neil. This is a photo from the last race of the Cup. So Team New Zealand sort of rounded ahead after that run, and unfortunately we sort of all watched Oracle sail past us upwind, and you can sort of see them here sailing upwind, hull just out of the water, probably 30 knots plus boat speed at that time, and we weren't able to match that, unfortunately, in those last few races. So at this point I'm going to hand over to Neil, who's going to fill you in a little bit on the Oracle development and talk a little bit more in detail about the control systems on these boats. Thank you.
Thanks, Andy. I think that's a very good background there from Andy, and you can see the tremendous work Team New Zealand did, and really they did a lot of the pioneering work, particularly on the hydrofoiling side. I've been with the Oracle team during this last Cup. Prior to that, I've worked with Team New Zealand. I worked with Team New Zealand from '92 on and off, including when we took the Cup in '95 and successfully defended in 2000. I worked for the American One World team in 2003, and perhaps I should preempt any questions. My wife is a Californian, so I have some divided loyalties. Worked with Team New Zealand again in 2007 and joined Oracle when this event was happening. Tremendous challenge, and no blue-blooded engineer could probably resist the opportunity to work in a campaign like this. It's a tremendous leap forward from what we had with the old lead mines we sailed with. So, just skimming over quickly the way Oracle took it on. They came into the Cup with a tremendous legacy, particularly as far as the engineering and aero forces in the wing were concerned, and they had developed this massive wing for their trimaran in the deed of gift match against Alinghi. This boat only needed to sail 2 races to beat Alinghi and take the Cup back to America back in 2010. The wing they created is the biggest wing ever made on the planet. It's bigger than any aircraft wing, and it's a credit to the work they did during that campaign. Now, I wasn't part of that, but I've got a lot of admiration for the guys, particularly that drove that wing project through. As far as the 34 and particularly the hydrofoiling aspects, we adapted 2 AC-45 catamarans as test beds, much the same as Team New Zealand did with the SL-33s, and all that sailing was done in San Francisco. A lot of the components of all the boats that Oracle made this last time were in fact made here in New Zealand. many of you would be aware that they have quite a sophisticated boat building facility in Warkworth called Core Builders Composites, and everything except the hulls, in effect, was made, tooled, and by guys up in Warkworth. At some stages they would have had over 60 boat builders, nearly all of them Kiwis working there, so bringing some of Larry's money here to New Zealand. We had a strong, very multinational design team, based mainly in San Francisco, the people from Germany, from Spain, Italy, a few Americans too, and they had included the core team from Lingy, Dirk Kramers, Kurt Jordan, and a few other people there. So we had some people here in Auckland, largely working out of the core facility, and we did a lot of particularly testing on things to do with the Daggerboard control system. We built a particularly unique rig there where we could test a full-size Daggerboard in the workshop. We developed some pretty impressive low-friction foil bearings there on similar rigs. So what I'm going to try and do is talk more about the nuts and bolts of the design, particularly to do with the control systems and things to do with the Daggerboards and elevators and things. Look at the engineering aspects of the loads, the power you need to manoeuvre these boats and manipulate the foils, and explain how they work, how they manipulate the foils at various stages of the boat's track down the course, particularly the manoeuvres. A little bit touching on the forensics of engineering these things, finding out what went wrong when they don't do what you expect them to do, and I'll try to wind up with a bit of a comparison of the Oracle and Team New Zealand development approach. Now here's a little bit of video here from, I think, race 10, which features a nice jibe of the Team New Zealand boat out on the right there, and later on in the short sequence shows a nice roll tack of the Oracle boat. We learnt a lot from watching the Kiwis in action, and this is an example of it. Excuse me, I have to get to grips with driving this thing here. Try again.
Thinking, hey, we have pretty good pace against these guys.
This is Team New Zealand jibing, and you can see things going on all over the place. The crew are very busy. They're lifting the old board there. At this stage, Team New Zealand in race 10 were just slightly ahead of Oracle as they came to the bottom of the course. This is Oracle executing a roll tack on the next upwind leg. And here is the result of the end of that leg with Oracle just slightly ahead. In this case, Team New Zealand went on to win that race. They took this, the mark that they were just about up to, and took the outer course down to the bottom, and they managed to get ahead. There was more wind out there, so that was the second to last race, I think, that Team New Zealand won. Now, let's just have a look at what the boards are expected to do in several different aspects. Firstly, looking from the front of the boat, some people probably don't realise that the boards were actually lent in and out depending on whether you're going upwind or downwind. We call this canting. So on the left here you see the boat sailing with the wind on the left of the slide, on the starboard side of the boat. In that case they're going upwind. When you're going upwind, it's quite important to minimise the amount of side slip, or what sailors call leeway, or else it makes it longer and slower to get to the top mark. Perhaps this is not working at the moment. Anyway, on the right-hand side, you see what's happening when they're going downwind. And again, as Andy pointed out, the wind directions from the point of view of the crew on the boat are not that much different, upwind and downwind, with these really high performance boats. When you're going downwind, you can afford to actually cant the board over more, which increases the stability, and withdraw it out of the water a little bit too. So on most of the boats you had something like 10 to 15 degrees of range of cant, and the boards would be able to be pushed down into the water around about 3 metres out of the bottom of the hull. When you're going downwind, there's perhaps more like 2.5 metres. And then we turn 90 degrees to the boat. As Andy's pointed out too, the ride height of the boat is a very critical thing to maintain, and it's largely done by raking the board fore and aft around a transverse axis. In this case, you can see down there that there's around about 10 degrees total range available in that board. And the extremes of the pitch adjustment were used particularly during the manoeuvres to help pull the board down and drive it up. The side forces on these boats are phenomenal, and as you can imagine, with the leverage from the centre of effort, the friction in the Centrecase is a major factor to overcome. Now the rudders have got a horizontal lifting surface, which we call an elevator wing. They had to be kept at a setting, a fixed setting for the duration of the race. They could be adjusted, but only at the dock or not when you're racing. So you had to preset the elevators and just live with whatever you decided for the day. The fine adjustment of the pitch was done more in the straight line sailing to maintain that ride height, and ideally just to say a little bit a metre or so clear of the water. Now here's another little video, if I can make it work, that shows you in a little bit more detail what's going on during a typical jibe. To begin with, the boat's sitting here with the wind actually coming from the back of the screen towards you, and it's going to jibe around, and you'll see the foils moving during the course of the manoeuvre. So there you see that new board drop down into the water, and at that point it's been deliberately raked slightly aft or raked with a negative pitch. And they do that so that as the thing touches the water, it grips and gets dragged down. As soon as it's at the depth you need, it's necessary to rake it forward. So now you see it raked forward a few degrees, and then it starts to lift. The boat's swung through by the helmsman, and by this time the load is now transferred to the new board. And the old board, you just want to get that out of the water as quickly as possible to minimise the drag as you move forward. Oops, just go back there. Try that again. So we'll just run through this to the point where we're... Now the boat swung through, the load's transferring, the wind's now coming from the right, and they retract the board out of the water, and they have the board raked back in that case so that the lift helps drive the board up. And then right at the end of that sequence you see the board canted in, which is what you would do if you were about to do an upwind leg after the next mark. It's obviously easier to cant the boards when they're out of the water, not subject to the hydro forces. So how does that happen, particularly the up and down business to start with? The boards are housed in a Centrecase, much the same as dinghies and that would have, fundamentally. There's guide bearings inside the case there, and you can see here in the cutaway there's a bearing at the top, bearing at the bottom. They are typically more or less plastic material, though in our case we had developed rolling element bearings in there to help, and that cut the friction in there by about, to about 10% of what it would be without them. The case is not rigid in the boat, obviously, because it has to be able to manoeuvre the board up backwards and forwards. So the Centrecase has got what's effectively a big ball pivot position down the bottom, near the bottom of the hull. And as far as lifting the board up and down and positioning it in the case at the right height, this is done with, that's interesting. Okay. That's done with this, as two opposing lines. You can see the red line here is pretty obviously the line you'd use to lift the board. It's going around a little shiv on the top of the pole, which is part of the Centrecase. And the yellow line is opposing it, and it would drag the board down. Both those lines are led out around a couple of big shivs somewhere near that pivoting position and led forward to some mechanism to apply the load and move them. Generally, it's like an endless system. In the case of Oracle, out here, out of shot, we had a very large hydraulic cylinder which was double-ended, and one end was pulling the board down, the other end was pulling it up. More or less a continuous loop there. The down line, it's worth thinking about for a moment. When the boat's flying, and it's flying on one foil really, and there's something like 7 tonne needed to hold the boat up. Obviously this board, if there was nothing to stop it, would just get shot straight back into the boat. So the yellow line is actually the line that needs to withstand the biggest force, because that's holding the whole boat up when it's flying. The red line can afford to be a little bit less. It's basically taking the weight of the board. So now, when we think about now how do you actually apply those forces to manoeuvre the board, we only have the sailor's muscles at our disposal. And there's no motors allowed on these, and you're not allowed to use any stored energy of any form. So we had at our disposal 8 crew members, athletes, and Rob Waddell would be someone you all know. Rob and people like that can develop something like 3/4 of a kilowatt in peak bursts of probably up to 15 seconds, and they can sustain about 300 watts more or less continuously as long as you keep feeding them. So typically there'd be two guys on each pedestal, and they've got these coffee grinder type handles. And so when the two of them are working together, you can get 1.5 kilowatts, which is nearly 2 horsepower. So they're each equivalent to about 1 horse. And the power they put into the grinder at the top is led down to one of 2 things. In this back pedestal, it would be used exclusively for powering the winches, which control the wind sail or other sails on the boat. And in the case of Team New Zealand, the forward winches were used to haul the boards up and down. Oracle used hydraulics to drive a hydraulic cylinder to do the same thing. As far as the hydraulic power on the boat goes, both teams used 3 separate hydraulic pumps driven by the 3 other pedestals. The pedestals have got a clutching arrangement either at the top or in some other position, so that they can choose either to drive the hydraulic pump or drive the mechanical system to the winches. And in our case, there was a button at the top that you slapped to engage the pump, and in the other direction to engage the winches. This drive shaft running along here has got a whole series of clutches, right angle gearboxes and things to allow you to select to drive the power towards one or other winch, help someone else, join all 3 together. It's a very complicated business knowing what you're doing on this, and I know occasionally it's just total chaos on the boat. So the pumps themselves supply oil to drive hydraulic actuators, cylinders, and when we're talking about what's happening with the case, 2 of these cylinders in this example are used to control the canting laterally, and there's 1 cylinder on the front, just slightly out of shot, which is controlling the rake fore and aft. Here's another little example of what's going on. Here you see that case getting moved sideways. If you look for a moment there, you can see the two cylinders I just talked about. Here they've got a control valve associated with each cylinder. That control valve is in turn controlled by electrical signals from the buttons that the crew have at their disposal. On the front of the case, there's a third cylinder which controls the rake. And you see as it moves that it's quite a complicated movement going on there. That's why you need that ball joint at the bottom. So we'll look in a moment at quantifying these forces I just talked about, and basically they're coming from the wind load on the wing sail. The lateral loads on the sail are resisted by the lateral loads on the foils. The longitudinal loads, which are what's driving the boat forward, are opposed by drag loads on the foil. And those drag loads are much lower than if the hull was slap in the water there. Okay, so the control ram, which controls the rake, which is here on the front of the Centrecase, often sees over 2 tonne of load. In fact, our cylinders had to withstand up to 3.5 tonne of load sometimes. The boat, as we've said, probably about 6 tonne of the 7 and a bit tonne that the whole thing weighs is driven up this foil from the horizontal surface supporting the boat, and there's probably about 600 kilograms of drag typically at 40 knots. And then similar loads are on the rudders, but much smaller. As far as canting goes, the side force on the boat is substantial, and in this case here we have a load up here where the lateral rams are controlling the canting of around about 16 tonnes, and down at the pivot the reaction is over 20 tonnes. Now you can imagine that's a phenomenal torque being driven into the hull. You know, you've got 16 Toyotas hanging that way and 22 of them that way, and you've got a very lightweight tubular structure in effect there resisting it. And in turn the beams transmit that across the boat to keep the structural integrity intact. Now these diagrams are obviously schematics. They're very simplified pictures of what's really going on there, but they illustrate the global loads that are involved. And you can see that the foil itself has a complicated set of loads that you're dealing with, and in fact some of the loads on the bottom of the wing when you're going downwind with them canted are opposing the loads on the vertical side. And some people would have argued, well, this is counterproductive because these two Y1 horizontal loads are cancelling each other out to some effect, to some degree. But in fact, that tick type of shape that Team New Zealand pioneered is the secret to the inherent heave stability of the boat. As you can imagine, as the boat lifts up, not only can the tip of the foil come out of the water and shed lift, the boat's sliding sideways more and more, the more of the vertical area you're losing. And as it slides sideways, the angle of attack on this lower section actually lifts up ultimately to above the neutral section of the foil, and that also reduces the lift. So it's a double-edged sort of stability effect. There's a few little pics here of the real things. Our foils with Oracle had quite a large radius between the vertical and the horizontal section, which our hydrodynamicists were adamant was very important from a drag point of view. But it did mean that as you withdrew them up to the legally required height, the curved section started to penetrate into the hull. So we had to develop sliding skin here that followed the foil as it canted sideways. The curved section got hauled into the boat partially, and also of course with the rake it was moving fore and aft slightly. Our boat building team and you know, guys in the shore crew contributed a lot to developing some very clever laminating techniques and design for this stuff. Before they got it nailed, quite often the boat would come back with complaints from the crew that the boards by the end of the day were almost impossible to haul up. And when you lift the boat and looked up, you could see blindingly obviously why, because the board had cut its way through this carbon laminate here, and it was jammed in there in a big mess of nasty fibres and things. That difference I just alluded to in the radius, you can see here the Team New Zealand board there, and this boat's much closer to the camera of course, is substantially tighter curve there than in the Oracle boards. And that's a little feature, and Michelle Kilmerick, our foil expert, was adamant this was, you know, a significant advantage to have that sort of form to the foil. A few more details. On the helmsman's wheels, as most people have seen from TV footage, there's a series of push buttons distributed around there. They're all just duplicates so that at least one's close to his hand at any time. There's a button on the aft side and the forward side of the wheel. When he pushes the aft button, it moves the top of the foil forward to rake more negative and less lift, and vice versa or the other button. So in our case, Jimmy was the man in charge of that, particularly through all the straight line sailing we were doing. During the manoeuvres, the crew, other members of the crew took part in that too. Over on the left side here, we got some close-ups of the actual top of the case, and this big sort of rectangular structure was part of the guiding of the case as it canted in and out. And you can just see right down there in the right-hand corner the tip of one of the Cant control cylinders. The other one's over here. The pitch cylinder you can't see, it's down below the deck level. And it's all hidden under that big flexible boot, which is mainly there to keep the water out, and plenty of water comes over there. The cockpit controls were typically along the gunnel, alongside each cockpit position, there was a little control panel which had membrane push buttons on it. The green ones controlled things on the right-hand side, starboard side of the boat, and the red ones on the other. Typically, the buttons are labelled forward, aft for rake, up, down, and cant over on the right-hand side. The guys in this second cockpit were primarily responsible for controlling the foils during the manoeuvres, which was a very busy time, as you know. And Simeon, the main man there, had various buttons on the floor and a couple here on the side of the pedestal, which he danced a little dance on as we were going through the manoeuvre, while he was winding the handles and occasionally pushing some of these buttons and cursing and swearing in Dutch. And here we've got Tom Slingsby, who was sort of auxiliary helmsman. He'd sprint across the boat as one of the first people to take over the helm while Jimmy was going to follow him. And there he was also responsible for the rate at which the previously being used board was lifted during the manoeuvre, because the board on this side had been holding up the whole weight of the boat. As you go through the manoeuvre, the load is being transferred to the other board, but if you just hit the up button prematurely, that board will suddenly pop up on the boat. The net result is the boat can slap down, and then you've lost hundreds of metres on the opposition. And he got very good at controlling what was a very simple little gadget. There was a ball valve with a bungee holding it shut, and a piece of string up to a piece of wood which he's got in his hand there. And as he got through there, the main control valve was opened, the ball valve was holding the oil back, and as the boat eased through, he'd just ease that up and it would just let the oil dribble through, and after weeks of practice he just knew exactly what to do. and the whole thing was a much smoother operation. Team New Zealand had very much the same sort of thing, but using the winches largely for the up and down part. Now here's another little video sequence which shows you what can go wrong. Where are we? There we are. This is just a sequence in May. If you look in the distance, you can see Team New Zealand are over there, and I think Prada over here somewhere. This was another testing day. Everyone was out on the water, and we were just honking along here. This is video from the chase boat. It's a bit shaky, but just see what happens. Bang. Okay, so this is typical of a number of events that we got where we lost control of the boat suddenly, and largely to do with the pitch function. And I think there's one more. You can just see that suddenly there, the board flicks forward quite dramatically. Now that event, in fact, it turned out when we got, they had to can the sailing for the day that day because the board was just jammed fully forward and the pitch function on that side didn't work anymore. And when we looked at it, it was ripped out of its mounting, and what had happened, we'd hit some rubbish that was under the water, and it had hit the foil and just ripped the whole thing out. So that investigation was pretty straightforward, and you could see a little bit of the damage on the foil. But other times you'd get a similar effect, and it was a bit of a mystery as to what was going on, particularly when you're developing things in the early stages. Now, what I've got up here, and there's a few slides following this, which is to do with the telemetry that's coming off the boat. As you probably know, like in Formula One, hundreds of parameters off the boat are logged continuously at about 10 hertz. Well, faster than that, but actually 10 hertz is near enough. So every day when the boats were going out on test days, and even race days, the telemetry was recorded on a hard drive on the boat and through Wi-Fi to the chase boat. This is a test day in February, and this is the first boat once it was back together after its dramatic capsize. And what's happened here is the boat has gone out. You can see from this is a map actually of the San Francisco area, as you probably figured out. Our base was down here at Pier 80, and Team New Zealand and Prada shared a base up here by the South Bay Bridge, and Artemis was across the water at Alameda. The boat, you can see the trace of the boat's movement logged through super accurate GPS for the day. It's sailed round or dragged round to the front, sailed in the race course area for a lot of time, a little bit out further in the bay, and then typically, as happens in San Francisco, the wind picks up in the middle of the day, but it was fortunate that you could retreat into South Bay where the wind was usually more moderate. So what happened this day is right down, not that far from the airport, we had a near capsize or near nosedive, near pitch pole rather, and I've got a little bit of data here during that event. Now there's 300 odd data streams, but here there's about 9, which are mainly to do with the board system. So what you've got up the top is the actual angle that the board rake's at any moment, and this is a time scale along the bottom. There's a whole bunch of different things you don't need to worry about too much, but right down the bottom there's something interesting, which is recording the button pushes from the wheel. And the lower peaks are Jimmy asking for the rake to be pushed forward, and then the higher peaks are asking for the rake to come back. When it goes forward, the nose tends to drop. When it comes back, it lifts the nose out. So I don't want to spend too much time on this, but you get some idea of this sort of information you've got available after the event. In the evenings, we often would go through things if there's something dramatic had happened. Now, if you look at the picture on the right, which is coordinated with the cursor, you'll see just screenshots of what the boat was doing from a GoPro camera at the back of the beam. To start with, it's riding along quite nicely at about 33 knots. We go forward 6 seconds in the data stream, and you'll see that the boat's lifting out of the water slowly, well, fairly rapidly. It's not quite the same camera angle. So Jimmy down the bottom has done a couple of jabs on the wheel to just trim that down, bring the nose back down, because there it's nearly 1.5 metres out of the water, which is starting to get a bit unstable. So then he's, and that's had some effect, so another couple of seconds you can see the boat's dropping, and actually dropping reasonably quickly. At that point he decides, oh okay, right now we've got to counteract that, so he gives a jab to bring the board back, and that's the one that I've got the arrow there saying button push. In fact, another few seconds later, it's going even further in the water, and by this time Jimmy's getting worried because he's actually held his finger on that button all the time, but the boat still continued to just drop down and start to take water over the bow and even more. And by this time the boat's trimming 5 degrees out of horizontal, nose down, still doing over 30 knots, but the speed's dragging down because of the drag, and everyone's starting to think, oh no. Up the top though, there's some good news, because the top trace is showing that in fact the board system started to respond to Jimmy's commands down the bottom here. So the thing raked forward, nothing, then just started to rake back, and then finally came back quite rapidly. And you can see Jimmy's getting quite assertive now. Bang, 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 bang. And fortunately, the boat responded and pulled up. So by 20 seconds from the start, things are all back to normal. The crew's had a little bit of a whoops, but they're just back to business, and we found out about this back at the base when they returned, and the chase boat guys saw it, of course. And it wasn't quite clear why that happened until we looked at the data. Back here, the green trace is the system pressure, which, in other words, the guys are pumping away virtually all the time. Suddenly it dropped from 600 to 700 bar down to 52 bar. So there was nothing, there was no one home. When the electrical signals were telling the valves to open, the valves were opening, but there was no pressure behind them to do anything. And the guys on the front cockpit who were primarily supplying this pressure were just winding their arms off, because they knew by now that there was trouble happening, something's not working. And they were slowly bringing pressure back up. It turned out that in fact what had happened is, as we went into this period here, the trimmer on the wing had decided it would be a good idea to change the twist of the wing, which again is operated by hydraulics. And when he operated his valves, it sucked all the pressure out of the main system, and we didn't have anything to look after the rake control. And that's what this slide says. So we changed a lot of things around that time. We hadn't had a lot of time on the water by then. We'd lost 5 weeks when we busted our first boards to start with. 8 days of sailing further down the track. The crew got too ballsy on a very blustery day and rolled the boat in San Francisco Harbour and went out under, got sucked out under the bridge by the tide, brought back again. 12 hours of panic and trauma before the remains of the boat were back at the base. So we lost a tremendous amount of time there. And our boats were not back on water until February and April in 2013. However, at that time we were learning quick, and we separated the wing and board functions, changed a lot of things about the circuitry. And one thing we did in the end of May, June, and it got a bit of publicity later, was come up with a slightly better way of arranging the control circuit on the pitch control. And it really was just applying the principles that like power steering on a car or other servo systems. Here's a little picture showing, whoops, we'll go back. Okay, now I'm under control. This thing here is the actual hydraulic cylinder that's pushing the thing backwards and forwards. This is the thing that's able to put three or more tons into doing this job. It's great from the point of view of power, but as the system pressure changes, and obviously it does all the time, and the loads on the board change, this cylinder, once it gets opened up and pressure goes into it, is likely to move the thing in a slightly unpredictable fashion. If there's not much load on the board and happens to be a lot of pressure, it'll push it a long way. Even though Jimmy might have mastered just a split-second pump on the button, he was always getting different results, and it was these external parameters that were doing it. So we came up with this little system here where we transferred this thing, which is the main control valve controlling that cylinder, from just being nailed onto the side of the boat to actually being on the moving part of the case, and it travelled around with the case. And then we put an electrical actuator. This is just like a little stepper motor electrical stepper motor, which was linked to a linear cam which controlled the plunges on that valve. And what we were effectively doing was using Jimmy's signal to move that cam to where he wanted it to be. And so there he is, he's given it a jab. The cam said, yeah, maybe half a degree. It's all by judgment, but the cam went forward. That in turn actuated the valve supplying high pressure oil to push the case in the same direction, and then moved along and dropped back onto the cam, because that's where we wanted it to be. It's just the same as power steering in a car, very similar principle. And in turn, if he wanted it to come back, first the cam gets pulled back, the whole thing livens up, follows it, and there it is. And that's all it was, and some people thought this was computer-controlled, magic, automatic, rake and ride height system, but there wasn't anything more than that to it, really. And this was developed prior to the Cup. There was nothing really done to it during the Cup. Okay, so I've been talking for a long time, but I'd just like to list the sort of things that I think are some of the key differences between Oracle and Team New Zealand. There's pluses and minuses from both teams. Team New Zealand had a lot more time on the water, particularly to start with. They were in the water before us. They did all that tremendous work with the 33s. On the other hand, Oracle, during that period, we launched our boat probably, I think, 6 or 7 weeks after Team New Zealand had. The first day out, we broke our first set of boards. There was a design fault in the structure of the first boards. We didn't have any spare ones, and the next ones weren't due for about 15 weeks. And we had to make some very quick and nasty boards to get us back on the water. And both those sets of boards were in fact the simple L-shaped boards that Team New Zealand had in fact tossed out as a bad thing anyway, prior to them even launching their first boat. So we're way behind the 8 ball there. Then, as I just said before, after 8 days of sailing, the guys managed to roll the boat, destroy the wing, nearly destroy the boat, and we lost another 15 weeks. So by this time, Oracle, after they got over all this, got their boats repaired and the new boat back in the water, they were in a comeback sort of mindset. That was forced on them, really. Now the wings, there's no denying that Oracle had a tremendous legacy of experience in developing that massive wing for the Trimaran, and that was a definite plus in the Oracle camp from day one. Those wings, they were all virtually identical. We did consider and investigated the main element twist that Team New Zealand stuck with. We couldn't find any advantage. We tested it on the 45s. It meant a heavier wing, a more complicated wing. So very early we had a decision, which surprised us, that we wouldn't bother with twisting the main element. So the Oracle wings were relatively simple. They had a very nice twist control system developed by Dimitri, a French guy with the team, very talented mechanical engineer. So the wing, I think, was a big plus for Oracle, and ultimately that wing proved to be tunable during the Cup. The board geometry, there wasn't much in it there. I think Team New Zealand were always ahead on the board philosophy, the design of the boards for stability. But Oracle, I think, ended up with slightly thinner, smaller boards running at a higher level of stress. And that was partly because we'd had such a bad experience with the first boards. We invested a lot of time and effort into a big test rig to pre-test the boards before they went in the boat. And the board control system, I think, was reasonably slick, and we just talked about that a moment ago. So at the end of the day, there's not much doubt that the primary thing that got us to the Cup was the improved upwind performance due to the moding of the wing. The boat always had a lot of lee helm, which is not a good thing, and indicated imbalance in the boat. So Scott Ferguson and his wing guys, and a lot of the aero guys, knew that there were ways to tune the wing to shift the centre of effort aft and down. The downside of it was that the winch loads climbed through the roof, and the crew had already rejected the odd testing we'd done with that, because it meant they had to drop down to a higher ratio gear to handle that load. And also the trimmer himself had his work cut out. You might have noticed there was a lot of wraps on that drum, on the main traveller sheet. So it had been put to one side in the early days, but when it was obvious that we were behind the 8 ball, we just got back into it and made it work. And the crew were grinding slower, but the load shifted aft, the lee helm went away, and the boat just lit up, upwind. The board control was pretty good, but there was nothing special about it really. And there was a bit of rudder elevator refinement. Our rudders were subject to a lot of cavitation. Jimmy hated it, a lot of vibration at high speed, and Paul Beca and his team did a lot of good work during the Cup even, putting fairing shapes at the intersection between the elevator and the vertical part of the rudder. So that's my last slide, and it's an attempt to talk about, just summarise what the event was like. And there's no denying the America's Cup, as it turned out, that last few weeks of the actual Cup was stupendous and probably the best Cup ever in 162 years, and closest racing, most lead changes, highest speeds. These are all sort of quotes that you'd see in the media. Biggest audience ever to watch. In short, it was fantastic. So,
yeah, the AC72 class rule with foiling wing sail multi-hulls certainly pushed the technology from previous America's Cups, order of magnitudes more than what it had, and the spectacle of the racing was very exciting, the racing in the end. So I hope we've given you a small insight into one quite small area of the America's Cup campaign, and anyone out there, young guys, kids out there that are interested in engineering, it certainly can be a pretty rewarding career and quite exciting. We'd just like to thank IPENZ for the opportunity to talk tonight, and thank everyone for coming along and listening to us. Thank you.
Just as an adjunct to all that, I'm sure that a lot of you are quite curious about more detail. This set of references will be put up on the IPENZ website, but it basically points you at some very interesting things with a lot more detail. Daily Sail article about the whole AC32. Seahorse magazine virtually had a expose of the whole design process back in December and covered a lot of things I've talked about. Oracle actually opened up the whole thing in that regard. They didn't know real secrets at the end. And you can read about that in Seahorse. YouTube's got heaps of footage. But anyway, all these references are available at the website soon. And just thanks to these people, of course. Team New Zealand have been very helpful in supplying material. Chris Cameron is the photographer to New Zealand, and we've used a lot of images in this. Oracle gave approval for all the things you've seen there tonight, and YouTube has got acres and acres of footage, which is quite useful too.